for the notes today is something called exponential growth and decay. This is kind of an intro lesson into exponentials that you typically get in Algebra 1. And the equations actually look a little bit different. We're going to write these down, but know that if you've done exponential growth or decay, the equation has looked slightly different than what we're going to see here. This brings in the natural base e, so we're getting more practice with that. So here's what I want us to write down. That's exponential growth or decay. And let's just do this a equals, this would read a naught, so that's essentially your starting value, and then e to the power of k times t. So we can tell whether or not this is exponential growth or decay if the k value, say it again. Yeah, it's like it's a subscript. So it's like this, and you would read that, I think, a naught. That's e to the power of k times t. Okay, so when that value of k, and that's going to be your percent, if it's greater than 0, then the function models a growing entity, so that is exponential growth. If it is less than 0, then that is a decaying entity. Okay, like I just mentioned, a naught is the original amount to the power of k times t. Okay, and then k is a constant representing the decay rate. So jot down everything I have underlined there. Underneath these notes are just an exponential growth and decay graph. That's something we should already be familiar with. We have graphed exponential equations, so same kind of deal there. So not only are we going to build equations, but we're going to actually have to solve some of these equations, so kind of tying in what we did yesterday. And it ends up being a decent amount of calculator work. So once we get to that, I brought in an extra set of calculators. And so the goal today is going to be to have everybody using a calculator. If we don't get there, that is okay. And I'll go grab some extras once we get going as well. So we're going to start with some applications. So this says the graph in figure 3.22, so that's what we see over here, shows the U.S. population in millions of people for 5 selected years from 1970 through 2010. In 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. Find an exponential growth function that models the data for 1970 through 2010. So we want to think about what things do we know as of now, what things do we need to find? Because this doesn't give us a whole lot of information. So let's jot down just kind of that general equation. So A, so the amount after any given time is equal to A naught, which is that starting amount. We will always know E, that's that natural number, and to the power of k times t. So one thing that I know for sure that we have here is we have data at 1970 and 2010. Now, for t, that's going to be the number of years that have passed between that amount. So we're going to go 2010 minus 1970. And that gives us a time of 40 years. And then we're going to want to use the actual populations in those given times. So after 40 years, the population, so that's in 2010, is 308.7 million. When we started measuring the population, that starting amount, or A naught, was 203.3 million. Again, we will always know E. And so what I'm starting to figure out is we don't know the value of K. We don't know that growth rate yet. And so that's what we're going to solve for. and then time is 40. That's the number of years that have passed between when we first started measuring the population to where the population is in 2010. When we're solving for the exponent, this is exactly what we worked on last class. So we're going to solve for the exponent by eventually bringing in a log. So again, think about last time when we start as exponentials, and if we're solving, there should be a log step somewhere along the way. Now, before we get to that log step, we need to get this exponential term all by itself. So the first thing I'm going to do is divide both sides by 203.3. Now, here's kind of a weird thing for this, and just in math in general. We want to keep things exact. As soon as I take 308.7 and divide it by 203.3, that's going to be some decimal, okay? We can check it, probably some decimal that is really long. And so we're going to leave it in this fraction form to keep this as exact as possible for as long as possible. So we're going to work with this fraction the rest of the way through, making some of our calculator work a little bit more tricky. This is now equal to E, and then let's rewrite this as 40K. Doesn't really make a difference, but just a little more natural to do that. Cole, put the phone away. Thank you. So since we're dealing with E, again, probably best that we do natural log. So I'm going to take the natural log of both sides. And then natural log of E, the 40K. So I'll go ahead and show all the steps here. Some of you are going to recognize that natural log of E is already 1, so this is just 40K. But kind of going back to what we did yesterday, we took this exponent, made it the coefficient. So natural log of 308.7 divided by 203.3. And then it equals 40K natural log of E. Now the natural log of E, like I said, is 1. So this is 40 times K times 1. So we can just ignore the natural log of E. Okay, multiplying by 1 is not going to change the value of it. That's why we chose to take the natural log. So that way we didn't have to worry about log and just adding in another step here. So now to get K by itself, I need to divide both sides by 40, leaving us with K being equal to 308.7 divided by 203.3 divided by 40. And we need to figure out what that value is. And when you're working on the Math Excel, good idea to pay attention to how many decimal places it wants us rounded to. We'll round the 3 decimal places. I feel like that's been pretty consistent in Math Excel to say 3 decimal places. I'm sorry, say that again. Because as soon as I take the natural log of this number, it's going to be a decimal that just goes on for forever. So writing it like this keeps it exact. And that's so much of where we are in math. We want to keep our answers exact as possible for as long as possible. So had I taken like natural log of 308.7 divided by 203.3, let's see what that works out to be. I think this will be a good way to answer your question. So natural log of 308.7 divided by 203.3. I get, see how that's a really long decimal? And even if I wrote down every single digit to that 9, it is still rounded. The calculator stores it. It just only displays however many decimal places that is. But this calculator has this decimal stored for as long as that decimal goes on for. Okay, so that's why we're keeping it and writing it like this every single time. Now I need to take that and divide it by 40, so I can just press divided by. And it's going to take that previous answer, including every decimal place, including the ones we don't see, divided by 40, and I get 0.0104. We'll round to 3 decimal places and call it 0.01. Okay, and so that is the growth rate for the population here. So in part A, we're working on writing an equation, so let's go ahead and piece all this together. So A representing the entire population, and it equals the starting population of 203.3 and then e to the power of 0.01 times t, where t is the number of years after 1970. And so now we can use this equation to try to predict when the US population will be 335 million. So we're trying to predict the year that this is going to happen. So I'm going to plug in 335 in for A, and we're going to have to solve again. And I think this would be good practice for us to figure out, or how to practice some solving right now. So let's do that. Why don't you all try coming up with a value for t? I have a ton of calculators back here on the table, so feel free to come grab one. In fact, please do grab one, because we're going to do something with the graphing calculators where everybody needs their own. So grab one. Some of you might need to share. I really don't have any more. So we should have found that we're going to reach the population of 335 million after about 50 years. So when you plug it in the calculator, you get about 49.94. That's close enough where we can just simply round up and say it's going to happen 50 years after we initially measured the population. So that's 50 years after 1970, making that about year 2020. I have no idea how accurate that is. Does anyone know the population right now?
Of what?
The US?
Yeah.
Without Googling it? No? Carly, what you got? Shh. We would keep it rounded down, but we might say like somewhere in between year 2019 and 2020 would be a more specific way to say that. Okay? Good question. Okay, again, I don't know why the side conversations are continuing. It's like I'm just talking over people. And I'll just wait until everyone is done talking. Okay. We're going to move on, and a little bit different type of problem, but still exponential growth and decay. But the setup here is a little odd. And we actually have to use some problem solving skills here. So it says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half of the original amount. Okay, so that part is really important. We're not given a specific amount for how much carbon-14 we're starting with or how much we're ending with. We're just saying whatever the amount is, after this number of years, we have about half of it. And use this to find the exponential decay model for carbon-14. So let's again write down what do we know and what do we not know. So our equation is A equals, and then that A naught representing the starting amount, and then e to the power of k times t. One thing that can help with this is let's make up an amount that we have. Okay, I think it really kind of brings in how this equation is built. So let's pretend, and I'm just making this up, that we're going to start with 4 grams. I don't know. 4 grams. Okay, we'll just call it 4. So half of it. So half of A naught would be 2. And this is going to be the amount we have after 5,715 years, right? So it's taking 5,715 years for the starting amount of 4 to get to 2. And we can use these values. This is going to be the new A in the equation to start to piece together that decay rate. We should expect that decay rate to be negative because of it being decay here. So we're going to replace A with 2. That's the new amount after we have passed 5,715 years. So we have 4 equals, K is what we're solving for, times 5,715. Now, when we go to start to solve this equation, I would divide both sides by 4. And when I get to 2/4, 2/4 is just simply 1/2. So no matter what amount we would have started with and gotten to half, we're going to always get to this 1/2 and then e to the power of, this would be 5715K. So with the half-lives, you could actually jump to this step right here and move on from there to find the decay rate, right? When you think about a half, you're always going to get this 1/2. And the next step, taking the natural log of both sides, brings us to the natural log of 1/2, and then equals the natural log of e, and then 5715K. Now, just kind of a side note, if you want to memorize and kind of take shortcuts here, your half-life equation is always natural log of 1/2, and then natural log of e is just 1, and so it's going to equal the time times k. So this is your half-life equation. And that's separate from what we're really doing here. Okay, but in this case, we already have a value of t, so I'm going to still solve this, kind of ignoring this here, but this is something like when you're working on the Math Excel, you can simply plug in the time to this equation, divide natural log of 1/2 by that time to find the decay rate. And that's what we're going to do here in just a second anyways. So then with this problem, natural log of e we know is 1, so I'm left with natural log of 1/2, and it equals 5,715K. And so I just need to divide natural log of 1/2 by 5,715, making the decay rates. So natural log of 0.5, I could also type in 1/2, divided by 5715. Ooh. Does anyone know what this means? It's the graphing calculator's way of doing scientific notation. Okay, so this value, that e means times 10, so this is negative 1 point. Let's go to 3 decimal places, so 213, and then times 10 to the power of negative 4. So that e is essentially the calculator's way of saying times 10 to the power of whatever comes after the e. And so when we have this, it's telling us to move the decimal place 4 to the left. So that would create, I think, 3 zeros. So negative 0.000113. Let's see, 1, 2, 3, 4. Yep. No, because of it being in between the negative 1.2, the first one brings it in front of the negative 1, and then there's 3 more left. So just 3 zeros. Yeah, no. I think this value for k should work. We're not going to type this in. That'd be just a lot into the equation. So this one should be good. And Math Excel, again, will specify how many decimal places to round to. Okay, so the equation that we're working on here, to find the exponential decay model for carbon-14, it's still going to be the amount because, right, the amount depends on how much we're actually measuring or how much we start with. And then a naught to the power, and then e to the power of negative 0.0001213 times the time. All right, so now let's put this equation to use. It says in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated that the scroll wrappings contained 76% of the original carbon-14. Estimate the age of the Dead Sea Scrolls. Okay, so we're solving for the time here. So here's what we want to kind of keep in mind, and building this equation can be a little tricky. So our starting amount, we still do not know, right? We do not know the starting amount. It just said whatever the amount was, we're now left with 76% of that starting amount. So in this equation, the amount we currently have is 76%, so 0.76 of the original amount, so of that A naught. And we're going to use that in the equation to work on coming up with this age here. So we have 0.76 of the starting amount equals the starting amount, and then e to the power of negative 0.0001213 times the time. So this feels really confusing because of the A naughts. Think about when that was a number though, right? We divided both sides by that number. We're still going to do that. And when we do that, that starting amount or the A naught just goes away. And so we're left with 0.76 equals e to the power of negative 0.0001213t. And this is where we'll take the natural log of both sides. So natural log of 0.76 equals, natural log of e is just 1. And so we're left with negative 0.0001213t. And so our value of t happens after I divide natural log of 0.76 by that amount. I'm just going to plug that into the calculator. So natural log of 0.76 divided by negative 0.000123 is 2231.2. What's that? 1213, so let's try that again. Good catch. Natural log of 0.76 divided by, good catch again, negative 0.0001213. Oh, look how big of a difference that made. It's definitely a good catch. Which brings up a good reminder to pay attention to what you're plugging into the calculator. Even I make mistakes with that, and you're going to make mistakes with that. It's going to happen. So this many years after, or it's this many years old, I guess. We don't really know. We could subtract it from 1947 to figure it out, but we'd say that it is approximately, let's round this. We would technically round that down because it was 0.46. So we'd say about 2,262 years old. It's pretty old. Okay, we're going to do two more things, and we're going to save the big calculator work that I was planning on doing for Monday. So I'm going to take the first like 15 or so minutes on Monday to do some of this graphing calculator work. And we'll actually get you a little bit of time to work today in class. Okay, so the last kind of growth model we have here is called the logistical growth model. And this one actually is going to be kind of relevant if you look at the topic for the next word problem, modeling the spread of flu. So our equations, these are the same thing. Let's use this A again. Equals C, and then divided by 1 plus A, e to the power of negative b times t. What's nice about this equation will always be provided. In fact, for your test, I'm going to provide all the equations for you. And so like the compound interest, you don't need to have memorized. The continuous equation, you don't need to have memorized. I'll provide those for your test. Okay, here, I'll zoom in. The exponent is negative b times t. That's negative bt. We don't need to know what these individual variables are because, again, this will always be provided. So really, these problems, we're just simply using the equation. Plugging in a value ends up being a lot of calculator work. You know what? Just don't even write it down. We don't care. Because this is going to be provided anyways. So here's your equation. Go and write down this one. because we're going to put this one to use. And this is just a form of that logistical growth model. Yep. So it says the function f of t describes a number of people represented by f of t who have become ill with influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. And again, all of these problems, it's just going to be plugging things in, maybe some solving, mostly calculator work. Now, we do want to think about what some of these things represent, and this is where the problem is helpful. So f of t is the number of people, and t is the number of weeks after its initial outbreak. So part A says how many people become ill with the flu when the epidemic began. This actually can be a really easy problem where you don't need to do anything on the calculator, and you'll see why in a second. But basically, we want to find after 0 weeks, what value are we left with? So I'm going to plug in 0. I have 30,000. And then 1 plus 20 e to the negative 1.5 times 0. And again, we don't need a calculator here. This is e to the power of 0, which is 1. So it's 1 plus 20 times 1, so that's 21. E to the power of 0 is 1. So this part right here, e to the negative 1.5, negative 1.5 times 0. So we're taking e to the power of 0, e to the power of 0, or any to the power of 0 is 1. So this is really 1 plus 20 times 1. 20 times 1 is 20. 20 plus 1 is 21. And so the initial population that was infected is 30,000 divided by 21. So I guess we did end up needing a calculator. So quite a bit. It's 1,429 people if we round up. So when the epidemic began, 0 weeks, there were 1,429-ish people infected with the flu. I can't tell if you're asking questions or just chatting with a neighbor. Okay. Maybe they went on a trip. Who knows? That's something we can figure out later. Shh. All right, now, part B. And all you're doing is just wasting time. They're going to get to work. The more chatty you are, the less time you're going to have to work. Part B, how many people were ill after the 4th week? So we're going to plug in 4. In this case, I'm going to basically just plug everything into the calculator. So 30,000, 1 plus 20, e to the power of negative 1.5 times 4. Now, when you plug this into the calculator, probably best to do it all in one go. You're going to want parentheses around the entire denominator. And just to kind of keep things consistent, we're going to also plug it into the entire numerator. So I'm going to go 30,000 divided by parentheses 1 plus 20, and then e to the power of negative 1.5 times 4. And holy cow, basically the whole town. So that ends up being 28,583. So basically in this particular outbreak, okay, Avery and Elliot, you guys need to stop. After this outbreak, almost the entire town by the 4th week has caught the flu at some point. All right, and then part C, What is the limiting size of f of t, the population that becomes ill? What would it be? What's the most amount of people that can get sick in this town? Just the entire population, so 30,000. Okay. That's basically it for all the applications that require a lot of work. I've got one last thing to kind of touch on here. And then I'll also come around and pass out the test review to all of you. So one just kind of really important thing in math that honestly I wish I did more with you all. I know it's kind of my own fault, but is modeling data. So collecting data and then being able to build an equation from that data and make predictions based on it. So throughout this chapter, we've been working with models that were given. However, we can create functions that model data by observing patterns in scatter plots. That's what we're going to do on Monday. Is we're going to actually let the calculator, we're going to plug in the data, we're going to get a bunch of data points, and then we're going to find kind of like a line of best fit, and where it can end up being either linear, exponential, or logarithmic. Okay, so down here, all these figures show the scatter plots for data that are exponential, logarithmic, and linear. What you are going to need to be able to do is plot some of this data and then come up with an idea as to, is it linear, is it exponential, or logarithmic? If you know what the graphs look like, it's really not too bad. Okay, so you basically need to be able to look at all these scatter plots and say, hey, that's exponential growth. This one's shape of an exponential graph. Okay, and if we were to draw kind of a line of best fit, that's another way to kind of see this. Okay, then just the opposite, this would be logarithmic growth, logarithmic decay, linear growth, linear decay. Okay, so recognizing what the data looks like and knowing if it's exponential, logarithmic, or linear. So one quick problem here. Okay, it says the data in table 3.6, that's this over here, indicates that between the ages of 1 and 11, the human brain does not grow linearly or steadily. A scatter plot for the data is shown. What type of function would be a good choice for modeling the data? So you're actually going to have to plot the data both on the review and on the test. You're then going to look at the data and say, okay, what does this look like? Is it exponential? Is it logarithmic? Is it linear? What does it end up being? Well, this looks like it's growing really quick at first, but then it flattens out. When it grows really quick and flattens out, that is logarithmic. And obviously, the percentage of the adult-sized brain is growing, so it'd be logarithmic growth. That's it. Okay, you will have to do the plotting as part of your review and part of the test as well. Okay, we're going to stop there. I'm going to come around with your test review. I will post an answer key for this too. Yeah, I will. You do not need to turn the review in. Ooh, let me stop the recording.